In this video, I will go over the homework that follows the lecture on applications of parametric equations, and as always, I hope that you watched this lecture. And let's go ahead and jump right into the homework. Here's the homework, and here's the first problem. And what we have here is a baseball hit at an angle of 43 degrees off the ground. So this is the height of the baseball, and it's hit at 43 degrees. So this is your initial angle theta, being 43 degrees. And we're looking at the height after 1.1 second. And although we don't have to write the full set of parametric equations, we're going to do this just for practice. But here's the idea. We're going to break this motion into two components, the horizontal and vertical. And each of the components acts under different laws of physics. And the horizontal component doesn't have any acceleration. And if it wasn't for the air resistance, the ball, or gravity, then the ball would just travel indefinitely far. So it's not the horizontal component that makes the ball stop, it's the gravity of the vertical component. And the horizontal motion can be described using the following formula. It's going to be the initial position plus initial velocity with respect to x times t, and there's no acceleration, otherwise I would have added this component, but since there is no acceleration, I'm not going to. And this is when we definitely need to introduce the coordinate system, and we're going to introduce the coordinate system with the x-axis origin being right under the ball, and the y-axis pointing upwards, so that the initial position of the ball in regards to the x-axis is 0. And to find the initial velocity with respect to x, we're going to use some trigonometry here. We're going to take the initial velocity of 92 feet per second, and we're going to multiply it by, because we're looking at the x component of that velocity, we're going to multiply it by cosine of 43 degrees. And so plugging it all into this formula, we get what? 92 times cosine of 43 degrees times t. Now, the vertical component, on the other hand, will be expressed like this. And here we have a vertical acceleration due to gravity. So we're going to express it with a negative sign because it's pointing down, and it's going to be negative gt squared over 2. So the initial vertical coordinate of the object is 3.05. The initial velocity with respect to y is going to be this. So it's going to be 92 times sine of 43 degrees t times t, and we're going to subtract the g, which is, I was going to write 9.8, but we're dealing with feet here, so it's going to be negative 32 feet per second squared, so it's negative 32 t squared over 2. This is the parametric equation, and it would be totally appropriate for us to become curious and to graph it. So x coordinate is 92 cosine, and here I need to check something. What's cosine of 43? If I type cosine of, we need to convert it to the radians, right? So cosine of 43 degrees, it's cosine of 43 divided by 180 and times times pi. So this is how we convert it to radians. And this is times t, comma, 3.05 plus 92 sine of 43 pi over 180 times t minus 16t squared. And if we let t to just go indefinitely, let's start at 0. Hold on. I think I should have put parentheses here. And maybe here, just so there is no confusion. And now we can see the trajectory of the ball, right? So if you let it run for 10 seconds, it will fly pretty far, so it's not realistic. And it does hit the ground at some point. How far? Around 4 seconds, right? So this is the trajectory of this baseball, but the question here is asking us to find the height of the baseball after 1.1 second. So the only thing we have to compute here is what is y evaluated at 1.1, and that should be pretty easy, right? So we just need to take this, and actually, if you want to see the ball, hold on, let's do this real quick. If you actually want to visualize the ball flying, replace t with s and add the slider and let s to range from 0 to 4 in steps 0. Let's say these are the steps, and this is your baseball. So if you hit it, it's going to go, and if we change the scale, this is what it's going to look like from far away. It's pretty cool, right? So that's your baseball traveling. Now, what we were asked to find is we were asked to find the height at 1.1. So we just need to replace t with 1.1. And the answer is 52.7 feet. And we have to round to the nearest tenth, so 52.7 is going to be the right answer. Now remember, you could have saved some time by only considering the y component, but I showed you both just in case. Because another question that could be asked here, sorry, let's go back. Another question that could be asked here is how long will the ball travel? And to answer that question, you would have to find out when x of t is equal to 0, so you would have to solve like a trigonometric equation, and then t will be your answer. So it is important to be able to write both of the components. Anyway, let's move on. Oh, there you go, the maximum height. That's another good question. We have coordinate system. The ball starts here, goes this way. This is the initial velocity. V is equal to 86. The angle is equal to 25. And the initial height is 3.45. And g is 32 feet per second squared. And we're going to write again both of the parametric equations. So x of t will be equal to the initial value of x plus the initial velocity, which is cosine of 25 degrees times 86. So let me write 86 cosine of 25 degrees, all that times t. And the y coordinate will be expressed like this: the initial height plus the initial velocity and minus the gt squared over 2. G is being 32, means we subtract 16 t squared. Now, to find the nearest height means we have to, I guess there are two ways. Analytically, what we would do, we would actually, analytically, we would differentiate the y, and we would get this. And then we would set this equal to 0, because this is when the height reaches its maximum. So t will be equal to 86 sine of 45 degrees divided by 32. So this is my t of maximum height. And then the answer will be, we would just plug in that t into the function, and that will answer the question. So let's do that. However, I'm going to use technology. We're going to have, well, now that I'm using technology, I kind of want to use it to the max of its ability. So we have initial height, which is 3.45, and initial height goes right over here. We have initial velocity, and the initial velocity is 86, and initial velocity goes right over here. We also have the angle. So the angle is theta. But it doesn't like theta, so let's use alpha for initial angle, and then alpha will be right over here. And I think now this describes the motion of such baseball. So this is the graph, and we need to find where it reaches its maximum, right? So for that, on one hand, we can just look at the graph and we can evaluate the maximum to be around what, like 24.08, something like this, right? But to do it analytically, we're actually going to first solve this equation. So we're going to compute this t maximum height to be equal to, I don't know if it likes it actually, to be 86. Where did 86 come from? 86 is our initial velocity multiplied by sine of the angle, but we have to convert it to radians, right? And we're going to divide everything by 32. And I guess here it does make sense to introduce the gravitational constant. So in our case, it's 32 feet per second squared, but it could be 9.8. So let's do this here. It's going to be 1/2 of g t squared. And this is not my 32, this is actually g. Yeah. So it reaches maximum when t is equal to that. And now I just have to evaluate this function. At t max. And that's the answer. So the maximum height is going to be 24.09 feet. Is that kind of what we observed? Yeah, pretty much, right? So that's the answer. So the answer would be 24.1. Determine the number of cusps for the hypocycloid described by the parametric equations. And as I'm not myself fluent with hypocycloids, I don't expect you to be hypofluid with hypocycloids. So Desmos is your best friend here. And as long as you understand what cusp is, I think just graphing this, I want to save this because we may have another problem like that. But let's go ahead and graph this hypocycloid. We have cosine of t plus 6 cosine of t over 6 and sine of t minus 6 sine of t over 6. And t goes from, I guess t goes from 0, let's say, to 10 pi. And I guess not enough, 12 pi. Let's see what happens when we make it 18 pi. And it starts overlapping, right? So we count the cusps. We have 1, 2, 3, 4, 5, 6, 7. So I guess the answer is n plus 1, whatever number you see here. Plus 1, that would be my theory. So 7 is the answer. Alright, so they actually suggest using this formula, so figuring out A and B coefficients, which... So not everything of this form will give us a hypercycloid, right? So we have to be careful. This is not the right formula. The formula is a little bit more complicated, but I tried. Alright, number 4. Which is the graph for the... Okay, so some of them are not even hypocycloids. Is this even connected? Oh yeah, this one is connected, right? So the best way will be to graph it. What do we have? 5 cosine theta minus, rather plus, cosine of 5 theta over 4. Y of theta is 5 sine theta minus 4 sine of 5 theta over 4. And let's graph it. Oh. That's pretty cool. I totally didn't think of this as a hypocycloid. Wow. Is it this one? 1, 2, 3, 4, 5, 6, 7, 8, 9. Did I count it right? 5, 9. We have 1, 2, 3, 4, 5, 9. Huh. Pretty cool. How am I supposed to know that without Desmos? Have no clue. Unless you graph a whole bunch of those points or analyze hypocycloids analytically, which is not really the purpose of this class anyway. So let's move on. Another baseball. This time I'm just going to start writing the equation. If you're not comfortable with that, then go back and review problems 1 and 2. But x of t will be equal to x0 plus v0 x t. So it's going to be, in our case, 0 plus cosine of 27 degrees times the 40 and all that times t, and y of t will be y0 plus v0y times t minus gt squared over 2. So y of t will be 0.8 plus 40 times sine of 27 degrees minus 16t squared, and I'm missing t right over here. So that's the answer. I'm not sure how that happened. So let's type it up. 40 cosine of 27 times pi over 180 times t. And here we have 0.8 plus 40 times sine minus 16t squared. I'm a little nervous. What does it, what? Oh geez, it wants the degrees. Why would it want degrees? I don't know, but does it want the degree symbol? Of course, we're dealing with meters, not feet, so it has to be 9.8. I should have paid closer attention. I'm gonna use Desmos model that I created here to answer this question. So the initial height is 2.75. The initial velocity is 86. The initial angle is 35. The g is 32. So this is my model. Determine the maximum height. Maximum height will be obtained here. So I'm just going to answer this question. I'm a little upset with myself here. So here we have initial height is 3.1, initial velocity is 90, alpha is 45, g is 32, and I'm going to write the equation, so it's going to be this exact thing, right? Instead of v0, I'll type 90. Instead of alpha, I'll type 45. That's what they want. G is 42, so we're gonna put 16 over here. All right. So here I'm simply computing the output at 2.2 seconds. So all I need to do is let me copy this. And t is 2.2. So the answer is 73.1. So we're writing the equation. The angle is 30 degrees. V0 is 89. Here we have H0, which is 2.9 minus 16t squared. Oh, forgot this is sine. All right, so this was my punishment for not paying attention the first time. And let's move on. Let's treat this as number 6. All right. Which is the graph of cycloid given the parametric equation? And we need to look at the differences between the graphs. When theta is equal to 0, all of them are equal to 0. Okay. When theta is equal to, let's say, pi over 2, this is when y is equal to 0 for the first time. Cosine of 0 is 0. Cosine of pi over 2 is 1. So which one of them goes back at pi over 2? Hold on, am I missing something? Oh yeah, that's right, sorry. This is x and y coordinate. I think it would be better if we just graph it. And let's take a look. And what do we see here? At 16 pi over 3, this is so this is when the first return to the same point occurs, and it all happens at roughly 5 1/4. So once again, 16 pi over 3. And the height is also important, so it looks like it's this answer. my god, this 5 pi over 2 confused me. This is going to drive me nuts. Another round of punishment for not paying attention. Looks like this one, but yeah, it's the only one that makes sense. One, two, three, four, five, six, seven, 8, 9. So again, we're looking at the cusps. So this one is at 2 pi over 3, 2 pi over 3, right? And the height is at roughly between 0.6, 0.7. So 2 pi over 3. Which one of them looks like it cusps at 2 pi over 3? Two of this, right? And which one of them reaches the maximum height at closer to 1 than to 0? It's this one. And we have another one of this. So 9/7. So it's closer to 3 pi. So this one looks good. This one looks good. And but the height, the maximum height is closer to 3 than to 2. So it's got to be the first one. Okay. All right. And if you have any questions about this, please reach out.